Hello there guys, it is golden hour in the secret location, so we've changed colour to orange on the underlinings. It looks a little bit weird, doesn't it? But that's just how it is. That's just how Laplace transforms are. Sometimes you've got to underline things in orange, right? It's just how it is, guys. Just how you don't understand. Okay, anyway, enough of what is going on? Okay, inverse Laplace transforms. Let's go with it, guys. Let's go with it. So, what is an inverse Laplace transform? If you've Laplace transformed something, then you can un-Laplace transform it by inverse Laplace transforming it. So, it's just like the inverse of anything, you know, it's just undoing it. So, if something Laplace transforms to something else, then the inverse Laplace transform just takes you back. I'll write that down a little bit formally. So, basically, the inverse Laplace transform, which is denoted by a little L, like as always, but then a little -1, like an inverse function. I'm not on the screen, but you guys can understand what I'm saying. That's the kind of notation for the inverse Laplace transform, and it has this definition. The inverse Laplace transform of capital F of S is lowercase f of t, as you would expect, right? Because the Laplace transform of lowercase f of t is capital Fs. So it just goes backwards. It's just the opposite. Now, why would you want to do that? Well, in the next video, what we will be doing is actually solving a differential equation using these. So it's kind of like, if all of these videos have been random Marvel movies, the next one is going to be an Avengers movie, right? Because it's going to combine everything, if you want to use that analogy. I mean, it's the best I've got, guys. But this is what I'm saying. Why would you want to inverse Laplace transform something? For the moment, just take my word for it that it's important and useful to do, even if it doesn't seem like it is. So you're going to use it in the next video to solve a differential equation. The idea is, though, think of it right now as basically if you've got a function of s, what Laplace transforms to make that. That's what the inverse Laplace transform is. So that's kind of what it is. Now, there isn't any, well, basically, we're not going to look at the analytical way to do this. There is an integral that is very complicated that will do it for you. But as I say, that we're not going to do it in this video. It's just unbelievably complicated. So we will save that for another video. The way that we're going to do these inverse Laplace transforms is by looking at them, and I'll show you exactly what I mean. So let's just do an example, guys. Let's just do an example and you'll get the gist of it. Let's go on to the new page. Okay, so let's find the inverse Laplace transform of 6 over s. So in other words, what Laplace transforms to make 6 over s? That's the question. Okay, let's have a look. So how can we do this? All you want to do is you want to try and transform this into something where you do know the Laplace transform, because that doesn't really look that obvious, right? So this is what we can do. I'm going to write this as 6 times the inverse Laplace transform of 1 over s. Okay, so I didn't mention it, but just like how the Laplace transform is a linear operator, which means you can factor constants out of it, you can do that with the inverse Laplace transform too. So you can just factor constants out of it. You can split it, so the inverse Laplace transform of a sum is the sum of the inverse Laplace transforms, etc., etc. All the rules are the exact same, nothing too interesting. Okay, so we're going to do that. Now, you might know what the Laplace transform of 1 over s is already, but if you don't, let's write this as 6 times the inverse Laplace transform. I'm going to write s as s to the 0 plus 1, and I'm going to write 1 as 0 factorial. Okay, so I know it's a bit of a leap, right, because like, why? But it's because, guys, and this is true, let me, where's my orange? It's gone running somewhere, guys. Oh no, there it is. We know that the Laplace transform of t to the n is n factorial over s to the n plus 1. That's a fact. So if we go backwards, the inverse Laplace transform of n factorial over s to the n plus 1 is t to the n, guys. So in this situation, there's an n there, right, in the power. What is n here? Well, clearly n is the number 0, right? So this is the Laplace transform, or this here in the brackets, this is the Laplace transform of t to the 0, which is 1. So this is equal to 6 times the number 1, which is 6. So the Laplace transform of the number 6 is 6 over s. there we go, we've gone backwards, that's it. Let's do another example. Okay guys, got another example for you right here. We're going to find the inverse Laplace transform of 4 over s plus 2. Okay, so it is an s, just to be really clear, it's not 5. I'm always going to try and avoid use the number 5 if possible. It's an s there, so it's the inverse Laplace transform of 4 over s plus 2. Okay, how do we do this? Well, again guys, let's factor the 4 out, just because it's going to be easier. So we have that that's equal to 4 times the inverse Laplace transform of 1 over s plus 2. And then guys, and again I'll kind of explain my reasoning in a moment, but I'm going to write this as the inverse Laplace transform of 1 over s minus 2, right? Because that would be 1 over s plus 2. It's just minus minus. Why have I done that? Well guys, because the Laplace transform of e to the a t is 1 over s minus a. Any similarities? Well, yes, the inverse Laplace transform then of 1 over s minus a is e to the a t, going backwards. So this is equal to 4 times, and then what's this, guys? Clearly, these are exactly the same, but a is the number minus 2. So this is 4e to the minus 2t. And it's really that simple. So that's the inverse Laplace transform of that one. Let's do one more. The inverse Laplace transform of s over s squared plus 9. How are we going to do this one? Well, guys, this time we're not going to factor anything out. We can't really factor anything out. We can't factor the s out, of course, because s is a part of the Laplace transform. We can't factor that out. So we're going to need to do something else. Guys, I'm going to do something nefarious here. I'm going to write this as the inverse Laplace transform of s over s squared, and what is 9? Nothing other than 3 squared. That is what 9 is. And guys, what am I about to do? I've obviously, because I've just pulled this out of nowhere, right? What am I about to do? I'm about to drop some facts on you once again. I know that the normal Laplace transform of cos omega t is s over s squared plus omega squared. So again, they're in the same form. So the inverse Laplace transform of s over s squared plus omega squared is cos omega t. So this must just be equal straight up to cos of 3t. And it's really that simple. It's kind of like a one step or two-step situation for that one. So it's really not that bad. Now guys, you might be thinking, that's all well and good, it doesn't really seem that hard, but I don't think that I would be able to do that. Like, can I replicate this? All you have to do for these is just practice them. Realistically, if you have an exam on Laplace transforms, you will have a table of all of them, or you'll be allowed to take in some notes, a cheat sheet where you can write down all of the Laplace transforms. I would recommend writing them all down in that case. But really, all you have to do for an inverse Laplace transform is just go on your table, look at things that your inverse Laplace transform resembles, see if you can do some sort of manipulation, and you'll end up with it. And always, you can check your answer by then taking the Laplace transform of cos 3t or whatever it ends up being, and see if you get back to this. So all you're doing is you're kind of inversing your Laplace transform, and that's really all there is to it. Guys, make sure you definitely stick around for the next video, because we're actually going to be solving a differential equation. For the first time, we're actually doing something useful with the Laplace transform. So stick around for the next video, link in description, and I'll see you in the next one. Cheers.